It's my great pleasure to introduce Shunhua Jiang. Shunhua is one of the fellows this quarter and a graduate student at Columbia University. I think Shunhua's work very clearly falls into the core, mission and focus and motivations of the program. There's a number of exciting works on problems at the intersection of optimization, sketching, dynamic data structures, using this to solve some of the key motivating problems I talked about in the beginning of the week, things like linear programming, semi-definite programming, dynamic versions of linear system solving. And in today's show, we're talking about matrix data structures. This naturally builds upon a number of the things we've seen before, where we've talked about sketching and dynamic graph algorithms. This talk will talk about some analogs of these dynamic graph algorithms or dynamic problems for more linear algebraic problems, which in turn I use some of the sketching techniques that were introduced earlier and have had a big impact through optimization methods. So thank you very much. I look forward to your talk.
Thank you so much for the invitation, and thank you all for coming early in the morning. Today I'm going to talk about matrix data structures, but before we go to matrix data structures, let me first give you a little higher picture about how it fits in this whole bootcamp. So the motivation of many of the matrix data structures I will cover today actually come from speeding up optimization algorithms. So we know that there are many algorithms for optimization problems. They are iterative, and whenever you have an iterative algorithm, we can measure its total running time as the number of iterations times the cost per iteration. I very much mean amortized cost per iteration here. And there has been many extensive research on trying to bound a smaller number of iterations, many of which we heard in yesterday's talk. But apart from that, there's also the other side of research that try to decrease the cost per iteration. And the observation behind these research is that many of these iterative algorithms, optimization algorithms, are actually very robust, and many variables are actually changing pretty slowly. So instead of recomputing all the variables from scratch in each iteration, which can be expensive, we can use data structures to implicitly maintain many solutions. And then in each iteration, we just perform a faster update to it. And this will improve the cost per iteration. And recently, there has been a renewing interest in trying to improve the cost per iteration, which leads to many state-of-the-art algorithms. There are a lot of graph algorithms, and many of them use graph data structures and graph linear algebra that were covered in the previous lectures. But for optimizations with general matrices, many of them will use matrix data structures, and that will be the topic of my talk today. And just if you're curious, the two figures on the right here are made by Dolly by OpenAI, because there's some very complicated optimization problem behind that. I think it would be a good fit to put them here. Okay, so now let me first define what are the matrix data structures that we will consider today. So we will consider this very simple prototype problem where we wanted to maintain some matrix function under certain updates to the matrix M, and then we wanted to support certain queries to this matrix function Fm. So let me give you some examples. It can be basically any matrix function. For example, it can be the inverse, or it can be the matrix multiplied with some fixed vector, or maybe wanted to maintain the leverage scores of the matrix, or it can even be the solution of some optimization problem that involves M. And there are also many different types of updates. It can be an element update to the matrix, or update a column or row, or a low rank update to the matrix. And there are also many different types of queries. We can query an element of this matrix function Fm, or we could query column row of the matrix, or maybe we wanted to give you a query vector every time we make the query, and I want you to output the matrix vector product. Okay. And sometimes in the query, we will allow approximations because it very much depends on what is the optimization problem that we need. So for different algorithms, it will give a different sort of interface when we're designing data structures. And because it allows approximations, we can use all the randomized sketching techniques that Michael talked about. And also because whenever we use randomness, we need to consider the adversarial update model. This is because these optimization algorithms are in some sense inherently adversarial, because the update that you receive in the next iteration will depend on the query outputs that you gave in previous iterations. So basically your randomness are somehow inherently leaked in previous iterations. So you need to take this into account when we're designing data structures. And these two are some recurring theme when people are constructing data structures. Okay, so now let me first give you a very, very simple example of one matrix data structure. So we just wanted to maintain the entire inverse matrix of our matrix M under rank 1 updates of form UV transpose. So what should we do? If we do it naively each iteration, we just recompute the inverse, and that would take n to the omega time, which omega is fast matrix multiplication exponent. But we can do it faster using this Woodbury identity. I think many of you might not be familiar with it, but it will come up multiple places in my talk today. So I think it's good to show it up here in the second slide. And I also made a little figure of this. So what it says is that basically if we wanted to compute a low rank update inside our inverse, we can take it outside of the inverse and it will still be a rank 1 update. So how to prove this, if you just multiply M plus UCV on the right, you will see that it equals to, like it just cancels out. Okay, so when we use this Woodbury identity, we can see that the main bottleneck is just a matrix vector multiplication. So it would only take n squared time for both update and query. Okay, so next, let me give you a small overview. It's going to be a very incomplete list of some of the recent better optimization algorithms that use matrix data structures. One big part of the optimization problems that I will cover today are conic optimization, where the formulation is we wanted to optimize some linear objective under some linear constraints, and with the extra hard constraint that the variable x should be inside some convex cone. The simplest and most well-known example of conic programming is linear programming, where the cone is just a non-negative orthon, and it's equivalent to say that we want the variables to be non-negative. And the current best algorithm for square dense LP, where this constraint matrix roughly have the same number of constraints as the number of variables, matches the current fast matrix multiplication time. So now it's n to the omega plus n to the 2 and 1 over 18. And these algorithms heavily use faster data structures. And there's also the other setting where we're in the flat case where there are much fewer number of constraints comparing to the number of variables. And in this case, the current best running time is nd plus d to the 2.5. So when n is large enough, when it's larger than d to the 1.5, this basically matches the input size. But there are also other conic programming. For example, another well-known one is semi-definite programming, where the cone is just a set of positive semi-definite matrices. And there's also sum of squares optimization, where the cone is a set of sum of squares polynomials, and the state-of-the-art algorithms all use faster data structures. But there are also, roughly speaking, matrix data structures can be applied for other regression problems or even for some non-convex optimization problems. If you have some other reference that you have in mind that also fall into this category, you're welcome to shoot me an email offline, and then I will add that later. Okay, so I won't, yeah.
What if the number of constraints is very large?
What if the constraint is very large? So actually, in this formulation, it doesn't make sense when it's too large. Yeah, you should have less number of constraints than the number of variables. But it's just this formulation. It's equivalent if you have inequalities in the LP, and then in that case, you can have more constraints than variables. Okay, so let me continue. Thank you for the question. I won't be able to cover all these problems today clearly. So today I will focus on two upper bounds. The first problem is linear programming because it's so well known and it's sort of very typical example of how to apply data structures. And the data structure for linear programming is inverse maintenance. And hopefully after today's talk, you will at least get to see how to get into the omega time for the current matrix multiplication exponent. And after that, I also wanted to cover this problem about dynamic least squares regression, not only because it's a very simple algorithm that can fit in one talk, but also because it uses some techniques that are also very useful in other problems like online leverage source sampling and JL sketch. So I think it would be nice to cover these techniques here. So that's the first two parts. And then after that, I will provide you with some matching conditional lower bounds for these two upper bounds. Okay. So let's get started with inverse maintenance for LP. But in fact, before I move on to the data structure part, I will need to first give you a little very brief overview about interior point methods for LP, because we are designing data structures for the algorithm. So we need to know what is the interface, what is the data structure problem that we care about. So this will be a very, very brief overview. I will hide a lot of details under the rug, and just in this afternoon, Yinyu will give a much more detailed 2-hour lecture about IPM. So you can think about my slide here as a little teaser for his lecture this afternoon. Okay, so we will consider this form of LP, where we have a primal formulation and a dual formulation, and then this is the primal feasibility constraint, this is the dual feasibility constraint, and we further require that the primal variables x and the dual slack variables x s to be both non-negative. And then there's this complementary slackness condition that basically says at optimality on every single coordinate, your primal variable should be 0 or your slack variable should be 0. And any x and s that satisfies the primal constraints, the dual constraints, and complementary slackness will give us the optimal solution, because this is all the equations that you need to get the optimal. But this is hard to solve directly because this is a quadratic term and we don't know how to solve that efficiently. So what we do in IPM is that we sort of relax this complementary slackness to say that we don't require x times s equals to 0. We just require it equals to some other number, mu, which is a positive number. And by the way, the dot here means coordinate-wise product. And then once you decrease mu from some large number to 0, it will correspond to a path in our feasible region. And what does the algorithm do? It basically starts from some large mu0, and each iteration, it gradually decreases mu so that it moves along, approach the optimal solution. Okay. And in each iteration, what we do, because we wanted to decrease this mu, so we will compute some update vector to the mu, which I'll call a delta mu here. And we wanted to make sure our new point, which is x and y and s plus this delta steps, still satisfy the central path equation. And then that will give us this system here. You will see that the second and the third one are actually easy to see if you just plug in x plus delta x and then s plus delta s here. But for the first equation, we are getting rid of the second order term. So if you just look at it here, there should be a delta x times delta s here. And let me also explain the notation. The capital X here means a diagonal matrix where its diagonal are the vector x. And similarly for capital S. This is a pretty standard notation in the IPM literature. And I also wanted to mention, maybe some of you have heard that IPMs will take a Newton step in each iteration. So this is equivalent to a Newton step, even though I'm deriving it from complementary slackness. So if you relate to yesterday's talk, IPM would be a second order optimization algorithm. Okay, and I also wanted to say, it takes Rudin iterations in order to decrease your duality gap or like optimize your optimal value by half. So in the end, we'll take like Rudin times log 1 over epsilon iterations. I won't explain why we got Rudin here, but I think you will cover this afternoon. Okay, and we can equivalently write out these equations in the matrix form, and it will give us this matrix here. So the takeaway of this slide is, in IPM, in every single iteration, all we wanted to do is to solve some linear system where the s and x will depend on your current variable, so they will change each iteration, and we will compute these deltas, and then we'll take a step. So any questions for this slide? Continue. So we can also, from that linear system, write it out as the delta x as y as the inverse of m times some vector v. So that's why we need inverse maintenance, because there's an inverse here. Okay, so next, the IPMs are actually very, okay, go ahead. Oh, sorry, question. So IPMs are actually very robust in the sense that you can see in this figure, we don't really have to follow the central path exactly. It suffices for us to stay in some neighborhood of the central path, and it's enough to make progress. And not only that, there's also this observation like a long-standing observation that the variables are changing very slowly in the sense that the L2 norm of these delta steps are very small. And because in each iteration, we actually don't need to take the exact step. So what we can do is that each iteration, we only need to update a few entries of our primal and steel variables that have changed by a lot. And for all the other coordinates, we can just let them stay the same. So we can take a very sparse update in each iteration. And this means if you see our matrix M, the only part that's changing in M is this S and X here. This means in every iteration, we are updating only a few coordinates of the matrix M. This whole idea dates back to Badia in 1989, where he used this slowly changing and smaller update idea to get a n to the 2.5 algorithm for square dense LP. But in order to even bring it down further to fast matrix multiplication time, we will need a more clever amortization scheme. And it was first proposed by Cohen, Lee, and Song in 2019. So very roughly speaking, this is a very complicated amortization scheme, and it involves pretty complicated proof behind it, but I won't be able to cover any of them. But I will say that we can view this amortization scheme as follows. So for any j from 0 to log n over 2, why is this log n over 2 here? Because then 2 to the j is just root n. I'm thinking about we're taking root n iterations. So for every 2 to the j, there will be an update of size 2 to the 2j in every 2 to the j iterations. So let me show you in this diagram. So for j equals to 0, that means in every single iteration, we will receive a update that changes one element. And then for j equals to 1, it means in every 2 iterations, we will receive an update of size 4. And then for j equals to 3, it means in every 4 iterations, we will receive an update of size 16, and so on and so forth. Okay. And then as a sanity check, so we know like what is the update that we receive in iteration. Let's see what is the accumulated updates that we receive up to, let's say, the 4th iteration. So this will be just a sum of the like they're exponentially growing. So the last term will be the largest term. So basically for until the 2 to the j's iteration, in total, we will have accumulated some constant times 2 to the 2j number of updates. Okay, so any questions for the IPM part? Okay, great. So now we're ready to design the data structure. What we want from the data structure is that in every the updates of M will follow from this amortization scheme, and then each iteration we wanted to output a vector that's M inverse times V. Okay, so now I'm ready to present you the statement of the data structure, and then I will prove the statement of the data structure, and then we'll see how to apply it to combine it with the amortization scheme. Okay, so the data structure is that there is a data structure that supports the following 2 operations for n by n matrices. The first operation is an update operation, where we wanted to update the inverse of M to M plus delta, where delta changes k entries. And I claim that this takes tmat and k time, where tmat here is denotes the fast matrix multiplication time for multiplying an n by n matrix and an n by k matrix. And I should mention here, in fact, inside this notation, the order of the 3 numbers doesn't matter. So n and k equals to nkn and everything. That's from the literature of fast matrix multiplication. So I will use it pretty loosely in my talks. Sometimes I will change it to nkn, but it's the same number. And the second operation is a query operation where we don't actually perform the update, but instead we will have some small update on the fly, and then we just wanted to compute the matrix inverse times the vector. And I claim that this is cheaper than the update operation. It only takes k omega plus nk time. And as a figure here, whenever we're going to compute the update, we actually add these updates to our matrix, and then we compute the new inverse matrix. But when we are going to perform the query operation, we don't actually add them to the matrix. We just compute it on the fly. And another diagram to think about is that we have this maintained matrix M, and there's this current M that gets updated in every iteration, and then we accumulate all the changes in the delta. And only when we have accumulated enough updates in the delta, we will actually perform an update operation. Otherwise, we just use this query operation on the fly. There will be some threshold into the A where A is smaller than 1 that will be set later in order to balance the running time of the two operations. Okay, so next, let me tell you how to implement these two operations. It's actually, yeah.
Are you maintaining exactly or just
we are maintaining it exactly.
And you don't encounter precision issues?
There are other papers that will deal with precision issues, but I'm not going to cover that in my talk here. Yes.
Yeah. I think in numerical analysis, people say that you should never explicitly maintain the inverse matrix. And to quote Sushant from his first lecture, if you're maintaining M inverse explicitly, you're doing something wrong. Do you think it's is it a problem? Or can one?
I don't think it's a problem here, just because we're in the high precision regime instead of using those iterative linear system solved here. So we're already in the high precision regime, so we can
You're assuming fast matrix multiplication, and you're not assuming sparsity, so it's kind of a theoretical result.
Right.
It is very much a theoretical result.
For instance, there are numerical analysis results that argue stability. Right? They actually don't get blow up in the entries, etc., etc.
So,
Let's trust me. I'm wondering.
I think there's a recent paper on analyzing the bit complexity of all these operations, and it shows that I think you blow up by some like polygon factors, and all the results.
I see. So stability.
yeah, and another way I think about it, correct me if wrong, there are experts here, is that it sort of corresponds to the case where you have very ill-conditioned system and you want to solve this linear system. And I think in that case, all the iterative methods will depend on the condition numbers. They are not better than just compute the numbers. Yeah.
Just to make a quick comment to reconcile the things between the talks that I feel like I can comment on. I guess if you just want to solve a linear system, then you maybe don't need to fully form the inverse. And if you have better approximate representations, that's helpful. That's like synergistic with Sushant's talk. And even here, we want to solve m plus delta. We're not exactly forming the m plus delta inverse. You know, it's keeping track of a certain low rank factorization of it. I would say maybe that's the.
So it's not explicitly stored at the end of the day, right? Because it feels as written. Right, and that's why I'm wondering, maybe there's a way of representing it not explicitly, but rather by some data structure that lets you invert it whenever you want.
Yeah, maybe.
More in line with what Shunhua was talking about.
Sorry, man, if we're explicitly forming the whole inverse, there'd be an extra like n squared from just writing it down.
Yes, but like when you're query, you just query an elements from it.
Right. So I'd argue this is not explicitly maintaining the inverse.
Okay,
It has this representation of the inverse that's useful for doing inverse matrix vector. Just towards making a connection between the talks.
Okay, thank you for all the discussions. Let me continue with how to implement these two operations. So for the update operation, they first make this simple observation that because delta only have k non-zero entries, so we can write it as some low-rank decomposition, u times c times v, where u and v both take some columns from the identity matrix. And then we will just directly apply Woodbury identity to it. And the hard part when computing Woodbury identity is this second term. So what are these matrices? So they are actually very simple because U and V are both like submatrix of the identity matrix. So M inverse U, V transpose time M inverse, and this middle matrix, they are all just some submatrix of the matrix that we already maintain. So we can just read them off. And then so this term here will correspond to this figure here. And the bottleneck to compute this equation is when we are in the end multiplying the two rectangular matrices together. And that would take Tmat nkn time, as what I promised on the previous slide. And then next, for the query operation, it's very similar. We again write delta as this formulation. And then we again use Woodbury identity. But now we don't actually update the inverse matrix. Instead, we only wanted to compute the vector. So we'll use the maintained vector that we have on the right, and then we write it out as this. So now the most time-consuming steps are two steps. the first step is that when we're computing the smaller inverse in the middle, which have size k by k, so that would take k to the omega time. And the second step is that now we have this vector on the right, so we just do matrix vector multiplication from right to the left. And then when we're multiplying some vector with this big rectangular matrix, that would take nk time. And this is the query time that we promised. This is the update time, this is the query time. So now we have this inverse maintenance data structure. Let's try to apply it to our IPM from this amortization scheme. So what does the algorithm do? The algorithm is what I explained previously. So the algorithm will maintain the inverse of some matrix M, and it will accumulate all the element updates in this matrix delta. And then when delta has accumulated more than n to the a entries, we will perform an update operation. And otherwise, in each iteration, when we're running the IPM, we just perform a query operation to output this matrix vector product. So what is the time of the update? Well, we just compute the amortized time. So there are, because we only actually call this update operation when you have more than n to the a number of size of the update. So we can sum j from a log n over 2, because this exactly corresponds to 2 to the 2j equals to n to the a, and then up to j equals to log n over 2. And this is the cost of the update operation. And then we can amortize this over 2 to the j, because it happens in every 2 to the j iterations. And then there's this property that this function is actually a convex function. So we only need to sum the two terms on the two ends. The smallest term is when j equals to a log n over 2, and this is t mat n to the a. And we can amortize it over n to the a over 2 iterations. And then for the other end, it's when this term is n. So it's t mat n, that's n to the omega. And then we amortize that over root n iterations. So this is the amortized cost of update. And for query, it's much simpler because we only perform a query when your update is smaller than n to the a. So we just plug in k equals to n to the a here, and this is the query time. Okay, so now we get this update time and this query time. We wanted to balance these two terms by setting the parameter a. So I need to provide a little more background about fast matrix multiplication here. So there's this fast matrix multiplication exponent omega that I already used a lot, which is the running time to multiply two square matrices. And then there's also this dual exponent, which is denoted by alpha. Alpha is the largest constant, such that multiplying an n by n matrix with an n by n to the alpha matrix takes n squared time. So the smallest, like, it's very trivial that you can multiply a matrix and a vector in n squared time, but actually alpha can be much larger than that. There has been very active research until like this year. So it's currently the best omega is about 2.37, and the current alpha is about 0.32. So when we're using these algorithms, we just set a equals to alpha so that this t mat n to the a will be n squared. And then we just plug in them into these equations, and then the dominating term is n to the omega minus half here, and then multiplied by the total of root n number of iterations. This gives the claimed result that the algorithm will run in the current matrix multiplication time. But there is no reason to believe that these numbers are the true numbers, because you can see I have a citation that this comes up this year. But we do know that in the ideal case, omega should be at least 2, because that is your input size, and alpha should be at most 1. So what would we get if there are, like, in the future, when there are more improvements for fast matrix multiplication? And in the ideal case, we can balance these two terms by set a equals to 2 over 3, and both the query time and the update time equals to n to the 1 and 2 over 3, and that will give a total time of n to the 2 and 1 over 6. So there's still a gap here of size 1 over 6, and we can actually improve this to 1 over 18. But before I go on to that, and using a more complicated inverse maintenance data structure, so before I go to that data structure, there's one little detail that I kind of hid under the rug previously, which is that the entries of V are also changing. So what to do? So there are some different papers that use different techniques to deal with this. In the original paper by Cohen, Li, and Song, they just use some sampling technique on the vector v to make it have only rooted number of non-zero entries, so that whenever you're multiplying them, it only takes n to the 1.5 time, which is very small. And there's a later follow-up paper by Li Song and Jiang, where their techniques that you can use the sketching matrix that Michael talked about in his lectures, which have size root n times n. So it also sort of decrease your size to root n times n, and it will take n to the 1.5 time as well. And I should mention, because we are in this inherently adversarial setting, so they need to refresh the sketching matrix in every iteration. And then later, there's a paper by Brand where he made these algorithms deterministic, because if you're doing sampling or sketching, they are randomized by nature. And his observation is that the vector v actually follow the same amortization scheme as the matrix M. And then he says that we can write this slightly larger matrix with v, so that the vector that we care about, M inverse v, would just show up in the inverse. So we can basically just use the data structure I described previously for this slightly larger matrix, and then in the end, you just read off this column in this matrix. And more generally, in a later paper by the same author, he showed that actually for any matrix function that only involves plus, minus multiplication and inverse, we can rewrite it as the inverse of some larger matrix. So this inverse maintenance data structure can actually be used to maintain any matrix function that only uses these operations. Okay, so why am I saying these techniques? Because they are also useful when we wanted to further decrease this 1/6 factor. So let me continue to that now. So the 1/6 factor can be further improved to 1/18. It was first shown in a paper by myself and Song and Weinstein and Jiang, where our technique is a 2-level projection maintenance data structure, and we also need to use the sketching technique on the previous slide, and then we also need to generalize the amortization scheme to 2 levels. But later in the paper by Brand, he showed that actually we don't need to do 2-level in projection maintenance because of the matrix formula that I just described on the previous slide. So it actually suffices to use the 2-level inverse maintenance in a previous paper by Brand and some of his other co-authors. So let me describe this 2-level inverse maintenance data structure here. So high-levelly, what does it do? Previously, we were maintaining some matrix, and then we have the current matrix M. But now, instead of just maintaining one matrix, they will maintain a second matrix that sort of have a smaller distance between the current matrix M. And then the first matrix is maintained explicitly, same as before, but the second matrix is maintained implicitly, so it's more efficient. And then we will have the update operation to update the first matrix, and the query operations are still the same, but there's also an operation that I call partial update to update this middle matrix that's maintained implicitly. And then now we will have a new threshold that's smaller than the previous n to the a, which is the n to the b threshold, so that later we will be able to balance between these 3 operations to get a better trade-off. I won't be able to go into the details about all the data structures, but I do wanted to mention what do I mean when I say this matrix is maintained implicitly. So it means we are maintaining some transformation matrix T, which is defined as the matrix such that M2 equals to M1 times V times T. It was first defined by Stankowski, so it's a very late paper, about two decades ago. So why we wanted to maintain this transformation matrix? Because then when we're computing the inverse of M2, it's just equals to the inverse of the transformation matrix times the inverse that you already maintained. So it suffices to, if we have this transformation matrix, we already have this new inverse. And then we can compute the closed form formula of the transformation matrix. And the observation is that because M2 minus M1 is very sparse, it have at most n to the a non-zero entries. So together, after multiplying with M1 inverse here, this matrix will only have at most n to the a non-zero columns. So it has some structure here. And the inverse of the transformation matrix preserves that structure. So the inverse of the transformation matrix also only have n to the a non-zero columns. And when I say we maintain M2 inverse implicitly, what I meant is that we actually only maintain the inverse of this smaller sub matrix. Even though I won't go into details why that is efficient, but I hope you can at least see just from this formula here that the part that's actually being inversed is exactly the sum matrix. The other part, it's still C2 here, so it will make it more efficient. Okay, so I also won't give the exact statement of the data structure, but I will just give the application of this data structure to our LP problem. So the update time is the same as before, and then we get the second level partial update time. I hope it should sort of make sense to you because previously we sort of get this amortization over root into the A iterations, and now we'll get this amortization over root into the B iterations for our smaller threshold. And then the query time also improves from the previous query time, which was n to the 1 plus A. And then the root n here comes from the sketching technique that we were using because it's sort of equivalent to you were reading root n entries. Okay, now let's try to apply them. So in the ideal case, we have two parameters we can balance now. We'll set A equals to 8/9 and B equals to 2/3. And then all of this running time equals to n to the 1 and 5/9. And that will give the total running time of 2 and 1/18. So the natural question you should have in mind right now is, okay, can we try to further generalize this data structure to more levels to make it more efficient? Well, first of all, there are some technical reasons why this might be hard. One is that we're already maintaining this second level matrix implicitly, and it's kind of hard to imagine how to do it even more implicitly in the third level and more levels. And second is that we are already using this sketching technique that reduces the dimension on the left. And then we also exploit the sparse vector update on the right. So we do need those lower dimensions on the two sides. And it's a little hard to imagine where is the third side because you only have two sides of the matrix. But not only because of that, there's actually more evidence that it really might be hard to generalize this more. I will be very careful about the condition lower bound here because it is not a lower bound for the LP problem itself. Instead, we are using this data structure, applying it for the LP problem, and then we can also apply this data structure to other problems. For example, if we only allow element update and element query in each iteration, it's different numbers of updates and queries. So it will also give different running time. For example, you can see it's amortized over into the A iterations because you have element-wise element update. So there is a conditional lower bound for this data structure that apply for element update and element query in each iteration. And I should also mention, so this data structure not only have application in LP, it also have application in many other problems, for example, many graph problems. Yes?
It's a simple thing. You say M2 is the second level matrix. Is that the same as C2 from the previous slide?
So I'm saying we are maintaining it implicitly. It's not the same as C2, sorry. So when I say we maintain it implicitly, it means that this is C1 inverse. My notation might be a little confusing. C2 is just the name of the other block. Yeah. Yeah, so it can be used for many other graph problems as well. One application is that it can achieve a n to the 1.41 update and query time for dynamic reachability. I think in the fine-grained complexity talk, they mentioned this upper bound, but without giving any proof. So now you know how to get it by using the two-level inverse maintenance data structure. And then there is a conditional lower bound based on the hinted UMV conjecture that exactly matches the upper bound. So this is a lower bound for the data structure itself. So maybe we can still do something better for LP because we're considering a different problem and we also allow more approximations there, but it's unclear. So this is just some evidence that this might be hard. Okay, I will talk about the lower bounds in more details in the third part of my talk if I have the time. Okay, and then before I move on to the second part, I also wanted to just broadly go through some other data structures that are also used for similar problems. The first one is for flat LP, which is also a very important problem. So for the flat LP, the current best running time have this dependence n times d, so it's linear in n. And it means that we cannot afford to have root n iterations and also have some cost that's linear in n in every single iteration. So for these algorithms, we don't use the previous log barrier that gives the root n iterations. Instead, there's a better barrier designed by Lee and Sidford, the Lee-Sidford barrier that will give us root d iterations. And not only that, In order to get this linear dependence on n, we also cannot afford to use the sketching technique that we talked about previously, which will reduce the dimension to root n, and then you get n to the 1.5 cost iteration, but that's already more than linear. So they will need to use some vector maintenance on the left to do this more efficiently and get rid of the linear, like more than linear dependence on n. So there are a lot of data structures here. So because the least disparate barrier use Lewis weights, so you also need to maintain those Lewis weights efficiently. There are more data structures there. And then for the graph problems, there's also, like, first, I would think about them in some sense as special LPs, because this sort of is LPs where your matrix is Laplacians, and there are all the techniques to work with Laplacians. And for other structured LPs, for example, for LP with small true widths, there are more specialized algorithms for that can achieve linear time to solve the LP when the true width is small. And for other chronic programming problems, the inverse also have other structures that can be exploited by other data structures. I just wanted to give you a sense that for different optimization algorithms, you need to really see what is the special structure of the optimization problem and try to define specialized data structures for that. Okay, so next, let me see. Let's move on to the second part of my talk, which is about dynamic least squares regression. So this slide is to introduce least square regression, but I think it's already covered in Michael's talk earlier today. So I just wanted to remind you, this is the problem formulation, and we have the closed form formula. And if we wanted to compute it exactly, it would take n times d to the omega minus 1 time. But often we're happy with an approximate solution, and then we can use all the sketching techniques that he covered in details. And then in the end, we can achieve near linear time in the input size, and we can even reduce the dependence on epsilon to logarithmic instead of polynomial. But here today, we will consider a dynamic least squares regression problem, where in this setting, the rows of A and the rows of B are arriving one by one online. So this is the incremental setting. And there are in total n number of iterations. We should think about n as much larger than d, think about as polynomial in d. And our goal is to dynamically maintain maybe approximate version of the least square regression problem with minimum update time. This sort of models this continual learning setting where you already trained some model, but you're continually receiving new data points, and you don't want it to retrain your model from scratch. Whenever you get new data, you want it to update it more efficiently. And let me introduce some notations. We will use small a to the t to denote the new row, and then we will use capital A to the t to denote the matrix up to the t sprung. Okay. So first of all, if we wanted to solve it exactly, what do we do? This actually dates back to the control literature where they called this Kalman filter. And the idea is simply just apply Woodbury identity to the normal equation where there's this inverse, and it would take d squared time to do an update. So over n iterations, it will take nd squared time. But we know that for the static problem, we can improve this to near linear time in the input size. Can we also do this for the dynamic problem as well? Well, the answer is yes, we can do this. For the incremental updates, we can get a running time that's roughly nza plus some polynomial factors in d and in 1 over epsilon. And if you remember, Satyapo gave this whole talk about working with adaptive adversary. So we can also make this work for the adaptive adversarial setting, but we will need to increase from d cubed to d to the 5th. Okay, so this almost matches the offline solution when n is very large. And I should also say, like, d to the 3 here is kind of natural because in the offline you would get d to the omega, but now we're in the online setting, so you get d cubed. It's sort of the same as what we would conjecture from OMV conjectures. Okay, and then how do we get this data structure? Well, one thing is you might want to try to just use those sketching matrices that make them dynamic, but it's a little hard to do this because the sketching matrix would depend on every single row that you have in the matrix A. So instead, we can use the sampling technique, Lowry score sampling. So this will be the third time in this week that you've seen this Lowry score sampling. But let me remind you what are the definitions. I think it was covered in great details in Sushan's talk earlier this week. So when we're in the graph setting, the leverage scores are called effective resistance, but it's called leverage scores for general matrices, and they're all the same thing. So they are defined as for the i's leverage score of a tall matrix A is defined as the i's row times this inverse and then the transpose of the i's row here. And then you can also think about them as the diagonal entries of the projection matrix. And intuitively, the leverage scores measures how important a row is for the row space of A. So for example, if the leverage score is 1, it means if you remove this row, you will decrease the rank of A by 1. And if all of the rows of the matrix A are the same, they will all have the same leverage score. And we also have some good properties. The first one is between 0 and 1. And the second one is that the summation of all the leverage scores equals to the rank. And then using leverage scores, we can do this leverage score sampling. It is equivalent to how we get this spectral sparsifier for graphs. And if you remember, Strand gave the proof of this statement here for graphs, but every single part of his proof would carry out for general matrices as well. So if we sample the ith row of this matrix with probability leverage score divided by epsilon squared, we will get a epsilon spectral approximation between DA and A. So in expectation, if we use this leverage sampling, we will sample D over epsilon squared number of rows. And because we are just sampling rows, we don't really mix them. This is very cheap to dynamize. And that I will show in the algorithm here. Oh, something wrong. But anyways, so what we do in the algorithm is that when a new row arrives, so first of all, we will maintain some approximate version of the exact matrix. And then when the new row arrives, we first compute the approximated version of the online leverage score. And then we just flip a coin with probability, this leverage score divided by epsilon squared as required by the leverage score sampling. And if we sample 1, then we will add this row as a new row to our maintained matrix. And then we update it using Woodbury. And otherwise, we just ignore this row and then throw it away. Okay, so if you see this algorithm, there are 2 steps that are expensive. The first step is when we're computing the leverage score, it would take D squared time in the worst case. The second step is this update. So let's first bound the running time of this second step because we don't do this update very often. We only do it when we are actually keeping a row. So there is this lemma in the paper by Cohen, Musco, and another author, I don't remember the name, where they say that the sum of these online leverage scores also is roughly D up to some logarithmic factors. So this means even though we are sampling in an online fashion, so it's not exactly the same as leverage score sampling, but still the expected number of rows that we keep still D over epsilon squared. So in total, we only do this update operations D over epsilon squared times. And each time we do this update, it takes D squared time. So this gives the D cubed term that I mentioned in the statement. And this is very small if you amortize it over poly n number of iterations. And now second is how to compute this leverage score efficiently. So this will use a JL trick that was first observed in the paper by Spielman and Srivastava for graph settings, but it will also work for general matrices. So the JL lemma says that there exists some JL matrix J that compress from dimension D to log n. So it's a very small compression, such that it can preserve the L2 norms of fixed n vectors x. And then the observation when we're computing the leverage score is that this is the definition of some leverage score. You can write it out as a L2 norm. So what we do is that we not only maintain the inverse matrix, we also maintain a JL sketched version of the inverse matrix. And whenever we're computing the leverage score, what we do is that we actually just use this compressed smaller matrix, multiply this with our new row vector, and then compute it out to norm, and it will be a good approximation for the leverage score itself. And then, so So basically, it will just take log n time because that's the size of your JL sketch and times the number of non-zero entries in the row. So this is the running time to estimate it. And that gives the first term LNZA in the stated running time. Okay. Finally, I wanted to add this slide about for adaptive adversaries just because we had the other lecture note. So I wanted to make some connections. So there are two parts why this is not currently working for adaptive adversaries. The first part is definitely this JL matrix as a random matrix, so you're leaking randomness. And the second part is that the online Larry score sampling itself is not adversarially robust. It's because the next row you receive, the adversary could see whether you have kept a row previously. So the next row it gives to you can depend on that information in order to attack you. So previously in Sushan's talk, when he was proving this Larry score sampling lemma, he said that we will use matrix turnoff bound. But now in order to make it work for this adaptive sequence, we will use the matrix turnoff bound for martingales, and there exist such results. But sadly, it's not. There's some subtle issues that makes it not as tight as the simpler matrix turnoff bound. So we will need to sample with a higher probability. So it needs to be d times the Larry score. And then in the end, this means we are keeping d squared number of rows instead of d number of rows. I think it's an interesting question to see if we can improve this to match the oblivious case. And for the second part, to make the JL trick adversarially robust, I think it would fall into the unique answers template that Sachapo talked about. But what we do is that we just make the JL estimate and overestimate. So whenever the matrix doesn't sample a row, it's actually equivalent to how the algorithm would behave if the algorithm doesn't use the JL matrix. Because from the output point of view, you're not sampling any rows, you're just doing the same thing. So it's a unique answer. And whenever we actually sample a row, that is when some information could be leaked about this JL matrix. And that at that point, we will renew the JL sketch, so discard the previous JL sketch, and renew our to fresh randomness. Okay, I think I'm running out of time, but is there any question for the second part?
Can you say more about why only you leakage only when the row is sampled?
What is only?
You mentioned that you leak randomness about the JL sketch only when the row is stricken.
Yes. Because otherwise, you can imagine I'm running two algorithms in parallel. The first algorithm is the one where we compute this thing using the JL sketch. The other one is I don't use any JL sketch. I just compute it exactly. And then when you are not sampling any row, both algorithms won't be sample any row. So they will perform exactly the same. So it's nothing.
Yeah, that's really literally doesn't see it.
Yes. Yes. Okay.
So you're saying when you pick it, you reweight it by what you sampled by, and that leaks what you sampled by.
When you're talking about the JL part or the JL part? Yes, so when you're sampled, it doesn't really leak very strong information. It's only a 1 or 0 information, but maybe because of you're using the JL sketch, you're sampling from a slightly larger probability than you don't use it, then you could be leaking information. Yes.
Thanks.
Okay, so finally, I'm going to provide some matching lower bounds for the two upper bounds that I talked about. And then both of these lower bounds are going to be based on OMV conjecture or variance of the OMV conjecture. Let me remind you the definition of the OMV conjecture. So first, it's about the online matrix vector multiplication problem, where in the beginning, we are given some matrix and then in each round, we are given some vector v, and then we wanted to compute the product of this matrix with the vector. Okay, and the conjecture states that there is no algorithm that preprocesses the matrix in poly n time, and it achieves less than n squared amortized query cost. There's no such problem. So roughly what it means is that in the offline setting, if we wanted to multiply a matrix with n vectors, we can use fast matrix multiplication to get into the omega time. But if we wanted to do it online, then we cannot do it better than n cubed time. So it also says that the only way to speed up matrix vector multiplication is by batching. So there are many conditional lower bounds for dynamic problems, especially for dynamic graph problems that we can prove using this conjecture, some of which you already seen in Ce and Yingzhan's talk earlier this week. I also want to say it also implies that the OU-MV conjecture is also hard, where in the OU-MV conjecture, you're not only given a vector V in iteration, you're given a U and a V, and you only wanted to output a scalar, which is U transpose MV. Even that is hard, and it's the same lower bound. Okay, so now we know the conjecture. Let me first tell you a variant of this conjecture that can be used to prove a matching lower bound for the inverse maintenance data structure. This is called a hinted UMV problem. So it's slightly more complicated. Let me go through it with graphs. So in the beginning, you are given not only a matrix M, but some vectors, some rectangular matrix U and some rectangular matrix V of size n by n to the A and n by n to the B. This n to the A and n to the B will exactly match the n to the A and n to the B threshold we had in the upper bound. And then in the second phase, you are given some index set of the rows of M. In the third step, you are given some index set J of the columns of the matrix M. And then in the last step, you are given two index I and J, and then we want you to output the UMV product of the ith row of U and the submatrix of M and the jth row of V. And the conjecture says that any algorithm must do one of the following three things, which are all the naive things that you can imagine. The first thing is you do some precomputation in phase 2. You just multiply this matrix U and the submatrix of M in phase 2. Or if you don't do that, then in phase 3, you need to do some precomputation that multiplies U and the submatrix of M and V together. So whenever you do this precomputation, later you can read up the solution easily. So if you don't do any precomputation, then in the fourth step, you just have to compute this vector matrix multiplication naively, which would take n to the A plus A B time. So this conjecture is definitely stronger than the OMRE conjecture, but it sort of captures the same intuition behind, which is the only thing you can do to speed up computation is by pre-computing everything, or you have to do it in an online fashion where there's no other acceleration you can do. So to apply this, let me first write out the upper bound that we have. You can already see they sort of matches. And the proof is also very simple. It's basically, if we wanted to solve this hinted UMV conjecture using the inverse maintenance data structure, we can just add some diagonal matrix, identity matrix in here and in here. And then in each phase, you just either perform an into the A update that updates into the, add into the A number of ones here, or you perform an into the B update that adds into the B number of ones here. And then in the last phase, you just do a query. So this means there's a lower bound that adds up these three terms together for the balanced cost of all these three operations. And that matches the n to the 1.41 upper bound that I described for many graph problems. Okay, so this is the lower bound for inverse maintenance. And finally, I just have one last slide about the lower bound for the least square regression. So if you see this upper bound here, you notice some difference between the static case. One case is that we have polynomial dependence on 1 over epsilon instead of logarithmic dependence. So can we do better? But we show this lower bound by the OMV conjecture that actually no. If you wanted to achieve very high accuracy, it will require this squared time. So you cannot get the amortized time per iteration. And another thing is that this upper bound only works for incremental updates. What about fully dynamic update where you have both incremental updates and decremental updates? So the answer is also no. So even if you just wanted to maintain some constant approximation, you will need to use the squared amortized cost per iteration. Okay, so finally I'm ready to end my talk. I'm just gonna slightly go over these three takeaways. The first one is that we've already seen there are many dynamic data structures that can be used to improve the cost per iteration of optimization algorithms. And for different algorithms, we need to design specific specialized data structures for them. And then there are, the second thing is that many dimension reduction techniques, randomized techniques are very useful, because often we allow approximations in the optimization algorithms. And the third part is that sometimes when your upper bound is stuck, it's also an interesting question to think about the lower bound. And we have this OMV conjecture, which is by nature pretty algebraic, and sometimes it's very suitable to apply that for our questions. Okay, thank you, and I'm happy to take questions.
Thank you. Questions?
Okay, so 2 questions. So first of all, is there any chance to improve the exponent on D in the online least squares regression, like from D cubed to maybe D to the omega or something like that?
We don't have any explicit lower bound, but I think it would be hard because my intuition is this D cubed fits with the OMB.
And the other question is, I guess things change significantly when you simultaneously add not only a row, but also a column. Do you think that there's any chance to get anything interesting in that regime?
Oh, good question. I have never thought about it, but I'm not sure what we would get.
Okay, thanks.
Yeah.
Any more questions? All right, let's thank Shunhua again. All right, so